Welcome to the online lecture that is going to discuss chemical bonding and Lewis dots. Before we get into bonding and Lewis dots, let's talk a little bit about AIDS. It's a disease that attacks the immune system, and for a long time it was a disease that was very scary and killing a lot of people. But in 1989, researchers discovered what's called the HIV protease protein. And basically this protein is critical to the virus's ability to replicate itself. So without this protein, the virus can't make more copies of itself inside the body. So therefore, HIV, the virus that causes AIDS, can't spread. All right, so in a picture, kind of a structural picture of it looks like this right here. Okay, so that's basically kind of the structure of this HIV protease protein. Now, once in 1989, once researchers kind of discovered this and mapped it out, drug companies set out to design a molecule that would disable this protein by sticking to what's called the active site. That's the site of the protein where, basically the action of the enzyme is going to work. And so in this case, the active site sits right here. All right, so they were trying to figure out some molecules, trying to design some molecules that would fit in that active site and not allow this HIV protease protein to work. And so what they did was they used what we call bonding theories, which are basically models that explain how atoms bond together to form molecules. So they use these bonding theories to simulate how potential drugs would interact with this protease molecule. So they sat and they're like, okay, what if we made a molecule that looked like this? How would it react with the active site of this protein? And they use these bonding theories in order to figure out which molecule would best bond to the active site, shut down the protein, and so the virus cannot proliferate inside of the body. Well, they finally figured it out and made a drug called protease inhibitors. Okay, and so basically what they do, and here's a picture of it right here in the middle, is this little molecule is in drug form, so it's either injected or swallowed in the body, and it goes and targets the HIV protease and basically sits inside that active site and doesn't allow the HIV protease to work in order to replicate. Okay, so it basically kind of just sits there and hogs the spot so that it can't spread in the body. So these drugs, they don't cure AIDS. Okay, so we don't have a cure to AIDS. But if basically if you have HIV and you take these drugs for the rest of your life, you can prevent this, more proliferation of the HIV virus, and you can basically live kind of normal, pretty normal lifespans now these days with HIV. But again, you still have HIV, so you still want to be cautious and not spreading it, to other people. So you can't just kind of, live life wildly or whatever. You still have to be conscious about that and know that this still exists in your body. All right, so what does this have to do with what we're learning in this chapter? Well, those same kind of bonding theories that researchers used in order to figure out how potential drugs would fit into the active site of these HIV protease proteins are what we're going to study. So we're going to study a particular bond theory called the Lewis model. And remember, bond theories predict what combinations of atoms are going to form compounds and what combinations don't. And these bonding theories will also, you'll see further in this chapter, help us explain the shapes of molecules. All right, so an example of the bonding model that we are going to use is the Lewis model. It represents electrons in atoms as dots, and you can draw dot structures, or what we call Lewis structures, to represent molecules. So here's a picture down here on the left is a picture of the individual atoms with their valence electrons shown as dots, and the picture on the right here is putting it all together in a molecule. So let's see how this works. So as you remember, valence electrons are the most important electrons when it comes to bonding two atoms together. So in the Lewis dot model, valence electrons are represented as dots surrounding the symbol of the element. So here's an example of the Lewis dot structure for the element oxygen. We can see that oxygen, if you look on the periodic table, oxygen has 6 valence electrons. All right, and around oxygen we have 6 dots. 1, 2, 3, 4, 5, 6. Okay, when we do the Lewis dot structure for an atom, what we always do is we fill the dots in singly first, one on each side, and then pair them up. So, for example, in this oxygen atom, we would do, 1 dot, 2, 3, 4, and then with the last 2, we would pair them up on each side, 5, 6. All right, so if we take a look at kind of all the elements in the second row of the periodic table, we can do Lewis dot structures for those. So lithium has 1 valence electron, so he's just going to have 1 dot. Beryllium has 2 valence electrons, so he's going to have 2 dots, 1, 2. All right, boron has 3, he'll have 3 dots, 1, 2, 3. Carbon has 4, so he'll have 4 dots, 1, 2, 3, 4, 1 on each side. So we always do it singly first, 1 on each side, and then we start pairing up. So let's take a look and see what that looks like. So nitrogen has 5 valence electrons because he's in group 5A. So he's going to have 1, 2, 3, 4, and then the 5th one's going to get paired up, 5. Similarly with oxygen, 1, 2, 3, 4. Oxygen has 6 altogether, so we're going to pair up the last 2, 5, 6. And then last but not least, fluorine, actually not last, but fluorine has 7, so we're going to do 1, 2, 3, 4, 5, 6, 7. Okay, and then here's last but not least is nitrogen, and he will have 1, 2, 3, 4, 5, 6, 7, 8, and that's not nitrogen, that is neon. Hello, and he's going to have 2 dots on all 4 sides, which means it's 8 dots altogether, and if you remember, neon is one of those inert noble gases that is not going to be very reactive, and we're going to see why when it comes to Lewis dot structures. All right, so let's start talking about chemical bonds. Chemical bonds involve the sharing or transferring of electrons to attain stable electron configurations for the atoms. So there's basically 2 main types of bonding, ionic and covalent. So if the electrons are transferred from one atom to another, then the bond is called an ionic bond. However, if the electrons are shared between the 2 atoms, then the bond is a covalent bond. But in either case, the bonding atoms attain what's called a stable electron configuration. And in this case, it's always 8 electrons on the outer shell. Okay, so that's why I was saying in our previous slide with neon, okay, we had 8 dots. Okay, 2 on each side. We can see that all 4 sides are filled with 2 dots each. So that is basically, it shows us our stable electron configuration of 8 dots or 8 electrons in the outer shell. And that basically, that fact is what we call the octet rule, where basically a stable configuration is 8 dots on the outer shell. All right, so let's take a look at this electron configuration for sodium and chlorine. So down here we've got sodium. Okay, he's got 1 valence electron, so he has 1 dot. And we're going to hook him up with chlorine. We're going to make a chemical bond between sodium and chlorine. Chlorine he's in a halogen, which means he's in group 7A, so he has 7 valence electrons. If you take a look, chlorine only needs 1 more electron or 1 more dot to become stable or full with 8 electrons. And if sodium loses his one valence electron, then that shell basically kind of disappears, and underneath he'll have a full shell. Okay, so it's advantageous for both of them to hook up. And what's going to happen is that sodium is going to transfer or give his electron to chlorine, so that chlorine gets a full octet, like we can see here, okay, with 8 dots. And sodium is going to have basically no dots, because that shell is going to disappear, but underneath it is always a full, the next full shell. So that's kind of basically how that works. Now, when chlorine gains an electron, he's going to have a -1 charge, because now he's got more electrons than protons in his atom. And likewise, when sodium loses his electron, now he is going to have more protons than electrons, and so he is going to have a positive charge. All right, and it's that positive and that negative charge between those two atoms that are going to attract each other to make a bond, okay, an ionic bond. So those two atoms will stick together because of the positive and negative charges between the ions. All right, so that's an example of an ionic bond. The other example here is of carbon tetrachloride. Okay, so here's carbon tetrachloride, and we can see that when we do the Lewis dot structure for this compound, all of the atoms are going to achieve stable electron configuration of 8 electrons in their outer shell. In this case, they're sharing electrons, and so the shared electrons are going to count for each atom's octet. So if we take a look, carbon in the middle has 8 electrons surrounding him, and each of the chlorines on the outside also have 8 electrons around them. Okay, so everybody has the stable 8 electrons in the outermost shell, and so that makes a nice stable what we call covalent bond in this molecule. All right, so in class we'll dive a little bit deeper into ionic and covalent bonding with Lewis dot structures. For now, though, what you need to realize or know how to do is the Lewis dot structure for particular atoms. So let's take a look at these 5 atoms and do a Lewis dot structure for each. So for phosphorus, okay, remember in a Lewis dot structure we always have the symbol for the atom, so phosphorus is P. If we look on our periodic table, phosphorus is in group 5A, so he has 5 valence electrons. So we're going to do 5 dots, 1 on each side, and then we'll pair up the last dot. So phosphorus looks like this. Magnesium, we're going to write Mg. Magnesium is in group 2A, and so that means that he's just going to have 2 dots representing his valence electrons, 1 on 2 sides. Similarly, potassium. Potassium's symbol is K, and potassium only has 1 valence electron, so he's just going to have 1 dot on one side. All right, we'll keep going with bromine. Bromine is Br, and bromine is going to have, he's in group 7A, he's a halogen, and he's going to have 7 valence electrons. So we're going to do 1 on each side, and then we'll pair up the other 3. All right, and then last but not least is selenium. Selenium's symbol is Se. He is in group 6A, and so he is going to have 6 dots, 1 on each side, and the last 2 will be paired up on 2 sides. Okay, so that's how you make Lewis dot structures for particular atoms, and that's where we're going to stop today in this online lecture. And when we get back, head back to class, we are going to take a look at covalent bonds and ionic bonds using Lewis dot structures.